Electrical work. Okay, we talked about prime movers before, but the prime mover in the electrical system is electrical voltage. So basically, if you want to get electrical work, all right, you have to have a voltage difference. All right, and this is what's going to cause the charges to move, or really what you're looking at are electrons. So it's basically what happens is when you just have an outlet, there's not an electrical difference. As soon as you plug something in that needs electricity, now there's a difference. It didn't have it, and the electrons have something to flow into. So that's what, it's the voltage that actually causes the electrical work. You can't see it, but you can see the effects of it. And one of the things you can also see is for your home, you have a meter, and you can tell how much electrical work is being done by how fast this is a little disc that turns around, has a little black mark on it, and you can see how fast it's turning, and you'll see that it turns pretty fast when you have a lot of things going on in the house, and it'll be slow when you have very little going on in the house. And these little dials here, all right, they click, all right, as you use up your electricity or your voltage, okay, and they measure kilowatt hours, and that's what that kWhr stands for. Okay, the equation for electrical work, is going to be the voltage difference times the charge moved. All right, now the variables. W for work. All right, the units will be a volt coulomb. All right, because voltage difference will be measured in volts. Charge is measured in coulombs. So a volt coulomb. And a short way to write that is joules. You've seen that before, right? We talked about work and energy. All right, change. You said about gravitational energy, when we had the change in kinetic energy or the change in potential energy, then it was equal to work. Okay, remember back then. All right, so voltage difference is V, and it's measured in volts. A lot of times we don't say voltage difference, but it's actually inferred in all the cases, except for when we get to thermal, we say thermal difference, and it has to be, or temperature difference, and it has to be that difference in there, because there is a difference between temperature and temperature difference. But here, a lot of times you just hear voltage. And then charge is the small letter Q. This is a tough one to remember. A lot of people forget that one, but it's a Q. And it's measured in what's called coulombs. Okay, another one we have is the charge. And this is an old one, actually. Charge is current times time. Charge is Q in coulombs. We just saw that. Current is measured with an I. This is another one that's tough to remember, and measured in amperes. And time is a small t, and it's measured in seconds. So if you need to find the charge, you take the current times the time, and it will give you the charge. One of the ways that I remember this one is quit. Now, it's not spelled correctly, of course, but Q and then equals I times T, quit. That's just something that I do to remember that one. All right, if you need the pyramids to help you, for the work equation, W equals V times Q. So that means that Q equals W divided by V. V equals W divided by Q. And over here, Q equals I times T. T equals Q divided by I. I equals Q divided by T. All right. Now, here's a tricky one for you. If we wanted to combine these two together, okay, and this is what this equation is right here. Work we know is V times Q, but Q is I times T. So I can take out the Q and substitute in the IT. So I have W equals VIT. Okay, that's a lot of times if you can do things in one step, it's a little faster. But that's how they're related. Okay, coulombs. All right. 1 coulomb is equal to 6.25 billion electrons. It's a lot of electrons. And 1 coulomb is equal to 1 ampere second. And 1 ampere hour is equal to 3,600 coulombs. Just some information so you can see that we're talking about a lot of electrons. A lot of electrons. And then if you wanted to talk efficiency, all right, it's the useful work done by a device divided by its electrical energy input. Okay, now a lot of times electrical devices, they have very low efficiencies. I mean, like sometimes as low as like 6%. If you're looking at a water pump, you know, you have all the systems in there. You know, you have your electrical system, you have mechanical system because you actually have like, it's almost like a fan in there, or there's baffles in there that move around. You have fluid because you're going to be putting water through, or some liquid, okay? So you've got resistance flowing through the pipes. And thermal, because with the electrical, you're going to have heat. And as it gets warmer, you have more electrical resistance. And it just kind of just goes on and on. So what happens is that some of them, electrical devices aren't very, very efficient when it comes to that. Okay, a solenoid. You probably have heard of these things. You have them in a lot of different places. But a solenoid, if you take a look at the picture, it's an electromechanical device. And it's mechanical because this little plunger here, it's actually a magnet, moves in and out. All right, so when you have things that are just moving, that's going to be mechanical. And then you have this coil that you see. And what you have here, if you look here closely, it says current. Okay, there's current moving through, so which basically it makes it a magnet. And this magnet is going to move in and out. Depends on what you're trying to do. All right. So you have the steel plunger. It moves in the hollow core of a wire-bound coil. So it's electromechanical. This is mechanical moving in and out. This is going to be your electrical. All right, this is made of steel or iron. It can't be made of aluminum because aluminum is not magnetic. And the plunger moves in and out of this coil of wire. Now, does it keep moving in and out? Not necessarily. All right. The higher the current flow, the stronger the magnetic attraction. Well, that makes sense, right? All right, some examples. The two that I like to give are, like, one is a doorbell. All right, your button for your doorbell would be here. All right, you push it in. Basically what it does is it completes the circuit and bring, okay, the doorbell rings. Okay, pretty simple. All right, the other one that I like to talk about is the washing machine. When you're washing clothes and it is spinning, if you ever listen to it, you'll hear that it's spinning around, and then all of a sudden you hear a click. All right, and then it slows down. That click that you hear is actually this magnet being pulled out of the coil so that the circuit breaks and it stops spinning. All right, I think that's pretty cool when you think about it. Probably the most common one that you hear talked about is probably in your car. All right, you have solenoids in your car. And you can see that there are a lot of other places too. Okay, I have some other things listed here. Okay, let's take a look at a problem. An automobile solenoid on a starter is active for 1.2 seconds. It draws a current of 15 amps at a voltage of 12 volts. So let's see what we have here. If it's in seconds, it has to be time. So it's 1.2 seconds. It says current 15 amps. Current is I. And voltage is 12 volts. Now it is assumed, all right, now I know what they say about assume, but it is assumed when it doesn't say voltage difference, but they mean a voltage difference there. All right, that is 12 volts. Find the total amount of charge moved. So we're looking for charge. So what's the equation? If you look back further in the PowerPoint, or if you remember, or if you wrote it down, all right, Q equals IT. Remember that quit I told you about? All right, so we need I times T. Well, 15 amps is going to be our I, and 1.2 seconds is going to be our seconds. So there you go, and you have 18 coulombs. All right, so we figured out how much of a charge we have. All right, then we need to find out the total number of electrons. All right, why? Because we know how to do it. That's why. Okay, so we know that if you have the number of electrons, like I said, this is an old piece here, Q times 6.25 times 10 to the 18th electrons per coulomb. That goes back into Unit 1 when we talked about voltage and how many electrons and things. So that's an old thing if you didn't remember that. So all you have to do now is you have to multiply your Q times that 6.25 times 10 to the 18th, and what happens is that the coulombs cancel out. This C cancels out with this C, and you're going to be left with the number of electrons. So, and notice here I have 112.5 times 10 to the 18th electrons. That is not really in proper scientific notation, but we did so that you could see where it was coming from. Okay, if you wanted to put that in proper scientific notation, you'd need to move this decimal 2 places to the left, and because it is a positive exponent, all right, that would go up to 20. So it would be 1.125 times 10 to the 20th electrons. That's proper scientific notation. All right, part C. Find the electrical work done. All right, so what's the equation for work? All right, V times Q. We had 12 volts. We found that you had 18 coulombs. Multiply them together, and you have 216 joules of work. Okay, well, that wraps up talking about electrical work for today, and have a good week.